Hello, everyone. Welcome to the GRASS FSI seminar series. Here today we have Scott Guan. He is a PhD student at Georgia Tech in the School of Aerospace Engineering. He is advised by Panagiotis Sieltrus. I don't know if you want to say that name again. He received his BS in aerospace engineering at Georgia Tech, and his research interest lies in machine learning, game theory, and optimal control, with his PhD work primarily focused in multi-agent decision making. So welcome again, and thank you for coming.
Yeah, thank you for inviting me, Chris. So I guess I'll just get started with my presentation. So hi, everyone. I'm Scott Guan from Georgia Tech. And I'm advised by Professor Panagiotis Sieltrus at the School of Aerospace Engineering. And I'm honored to be a guest speaker at the GRASS SFI seminar series. So in this talk, I will discuss a couple of projects I've been working on aiming to address the scalability issue in multi-agent decision-making problems. All right. So I guess we all know the application of the multi-agent decision-making, so I'm just going to skip this motivation part. So I want to now quickly talk about the framework that we use to model this problem. So we have multiple agents interacting with a potentially stochastic environment. At every time step, each agent take an action in the environment, and the agents transition to a new state as a consequence of their actions. And then each of them will receive a reward. So the goal of each agent is to maximize its own expected cumulative rewards, and the presence of other agents may have influence on the rewards and even the transitions of the agents. Then, in order to make informed decisions, an agent needs to reason what other agents may do. So I want to take this little crossroad example to quickly illustrate the idea, to more illustrate the complexity that we're facing in this multi-agent scenario. So with a single agent, whenever the agent takes this action going from left to right, crossing the road, it will arrive safely. In other words, the environment is stationary from that agent's aspect. However, when you have two agents, if the other agents stay in the middle of the road, basically this red vehicle, and this blue vehicle still goes from left to right, and then we're going to have a collision. So in this case, the blue agent really needs to consider the state of other agents before it makes its decision. So the story doesn't end here. Suppose now the two agents are both at the stopping line, and the blue agent needs to predict what the red agent will do. If the red agent is going to stay at the stopping line, then the blue agent can cross the road safely. Otherwise, if the red agent decided to also cross the road, then we're again going to have a collision. So in this multi-agent scenario, agent not only needs to consider the state of other agents, but it also needs to predict the behavior of others. So this really makes the problem much more complex than the single agent case. So in this talk, we will focus on the stochastic game framework to model the environment for the multi-agent decision-making problems. So in an n-agent stochastic game, we define the game through the following tuple here. So we have n individual state spaces and action spaces, each for a single agent, an n reward function, a transition function, and a discount factor. So the joint state space and the joint action space is defined as the Cartesian product space, and each agent's reward depends on the state of all agents and the actions taken by all agents, and then this reward function will give you a real valued reward. And then the transition function basically tells us, given the current joint state of the system and the joint actions taken by all agents, what's the probability of transitioning to a new joint state? So in this talk, we're interested in a class of Markov policy that is decentralized. So each agent observes all other agents' state, and then based on that, they're going to select its own action according to some probability distribution. So from this stochastic game formulation, one may already see the scalability issue. So one comes from the number of agents. So when you have a large number of agents, even if you have small state space and small action space, the Cartesian product space will still be very complex. The other one is simply the large state space. For example, if we only have 2 agents, but if both agents have 1,000 individual states, then the joint state space would be will have 1 million joint states, or basically 1,000 squared joint states. So the very last background we need is this solution concept of these stochastic games. So we will focus on the Nash equilibrium, which many may consider conservative, but at the same time, it's also very robust and simple. And sometimes maybe many people will think it's beautiful. So as we discussed before, each agent tries to maximize its own cumulative reward here. Notice that this cumulative reward depends not only on the policy of agent I, pi I, it also depends on all the policy applied by all the rest of the agents, basically pi minus I. So this will give us n coupled optimization problems. So one for each of the agents, and then when one agent maximizes, it also needs to take into consideration that all other agents are also maximizing. So this makes the problem really complex. So the Nash equilibrium is a set of policy pi star, such that any unilateral deviation from the Nash equilibrium will not increase the performance. So in this expression here, we have agent I deviating from its policy pi star to some other policy pi I, and while all other agents are still applying their Nash policy pi minus I star. And then you can see that this does not increase your performance. One can also extend or relax this notation to an epsilon Nash, such that any unilateral deviation from the epsilon Nash policy can at most give you an epsilon performance gain. So this basically covers all the background of this work, of this presentation, and hopefully, and I also promise you, the math will not be as intense later on into this talk. Now I can really present the outline of this talk. So it will basically be 2 parts, each addressing one of the scalability challenge. So in the first part, we will use a mean field game formulation to address the number of agent issue. So we will approximate a very large population game with a game between a fictitious player and the mean effect of the rest of the population. We will also present some convergence and epsilon Nash results for that. So in the second part, we will address the large state space issue. We will mainly focus on the 2-agent zero-sum game. We will utilize the divide and conquer idea and basically introduce a hierarchical decomposition approach and break down a very large game into multiple smaller games that are more manageable for us. So now we can get started with part 1. And also feel free to stop me if you have any questions. To motivate this mean field formulation, I want to first present these 3 pictures in the animal kingdom. So we have a swarm of fish, we also have a swarm of birds flocking, and a large population of migrating zebras. We know that these large population of animals sometimes make very organized behavior. So the question is, how do they make decisions in such large population? So the first characteristic of these large populations is this homogeneity. So the agents have the same or very similar state and action spaces, and they may also have almost the identical dynamics and the rewards. So all of these symmetries motivate us to really consider identical policies for all agents. The second characteristic is the extremely large population. So as a consequence, individuals are indistinguishable from each other. Individuals also have ignorable effect on the population behavior. So for example, if I remove 1 or 2 birds from this swarm of birds, it probably wouldn't change much the flocking behavior. So this motivates us to characterize the system state using the distribution of the agents. In other words, we may just need to keep track of what fraction of agents are in state S instead of documenting which specific agent is in which state. So these 2 observations are the main motivation for the mean field game. So when playing in a mean field game, an agent takes other agents as a whole and approximate its interaction with other agent as an interaction between itself and the mean agent of others. We will talk more about the sentence later. So before we really dive into the details, I want to present a roadmap for this mean field approach. So we want to obtain some kind of optimal policy for the finite n agent homogeneous system. We will first use an infinite population to approximate this n agent system. This is also known as the mean field approximation. And then we will find a Nash equilibrium for the infinite population system. So at first glance, an infinite population may be even harder to address than the finite n agent system. However, the infinite number of agents actually give us a very nice way to predict the behavior of the population, since it will zero out the noises in the dynamics. Then we will let the agents in the finite n population deploy this Nash policy we found for the infinite population system. In this case, we still have some guarantee that it will give us an epsilon Nash equilibrium. So it will basically give us the guarantee that by deviating from this policy we found, an agent can at most gain epsilon performance. So for the simplicity of this presentation, we will assume a decoupled identical dynamics. So this is an agent's transition depending only on its own state and its own action. It's not really influenced by other agents. We also assume a coupled identical reward for the agent. So the reward depends on other agent's state plus this agent's state and this agent's action. So the mean field approach is more general than this, but just to keep the notation simple and also the math simple, we just enforce these assumptions. So this approach is obviously not my original approach. So it was first proposed in around like 2006 and 2007 by a Canadian group and a French group. You can see the reference here. The original formulation is in a continuous setting. So one of the contribution of this work is to bring this approach to a discrete domain and address some regularity issue through entropy regularization. So we will first start with the first step, which is the mean field approximation. So previously, we argued that given a large population, the system can be characterized by the distribution of agents. Consequently, we want to first define the empirical distribution of the n agent system. So the empirical distribution is defined as follows. So this is essentially just counting what fraction of the number of agents, what fraction of agents are actually on node are on state S at the current time step. So for example, in this little resource distribution or resource allocation problem, we have 2 agents on node 1, so that's 2/4 of the agents are on state 1, and then 1 agent on node 3 and one agent on node 4. And then in this case, this is the empirical distribution of this system at the current time step. So notice that this empirical distribution mu n t is a random vector, since we have in general a stochastic dynamics. And this random vector could be very hard to propagate in general because you need the distribution of a random vector into the future to fully characterize this random vector. The other note is that for agent I, its own state Si plus the empirical distribution mu n t contains all the already contains enough useful information for it to make a decision. So for example, for agent 1, the little red agent here, whether it is agent 3 on node 4 and agent 4 on node 3, or it's agent 3 on node 3, agent 4 on node 4, it's the same for that agent because agent 3 and agent 4 are by assumption identical to each other. So this is basically, again, the reason why we want to introduce this mean field approach. Now we want to take this empirical distribution into for an infinite population system. So we define the mean field as the empirical distribution of the infinite population. The benefit of doing that is that the mean field now becomes deterministic due to the law of large numbers. So when you are averaging a large number of samples, then essentially you just get the average mean of your sample, right? So under the identical policy, the mean field has the following deterministic propagation rule here. So it is essentially the distribution propagation of a Markov chain induced by the agent's dynamics with a fixed policy pi here. And we're assuming all agents are using the same policy. Then I think it's quite natural for us to try to approximate the empirical distribution of a finite system with the mean field of an infinite population. So we do have the following lemma for doing this approximation. So this lemma basically states that the larger the population size, the smaller the difference between the mean field and the empirical distribution of a finite population. In other words, we can basically approximate the behavior of the finite population with the behavior of an infinite population. So now we have basically established the results for approximating this finite population with an infinite population. Next, we will see how we can find the Nash equilibrium for the infinite population system. So previously, we also argued that from the symmetry or the homogeneity of the system, we can assume that all agents are going to use the identical policy. So as a consequence, we want to introduce a fictitious representative agent that is responsible for generating the identical policy for all agents. And we will let this representative agent play against the infinite population. So the influence of the infinite population has on this representative agent is basically characterized by this mean field. Recall that we have decoupled dynamics, but a coupled reward. So this mean field will then induce a reward function for the representative agent. With the influence of the other agents captured in the reward, the representative agent faces a single agent optimization problem. Again, given this reward is fixed, given this mean field is fixed for now, the representative agent will try to optimize the following entropy-regularized cumulative reward function. So we added this entropy regularization term to provide all the necessary regularity condition for the guarantee of convergence. And we will not really talk about that in detail in this talk. So what happened here is that we have an inverse temperature, the beta here, and also the reference policy rho. This basically forms the entropy regularization. And then one can encode useful information into this reference policy, like a pre-trained policy or some kind of safe policy. And by playing with the inverse temperature, one can control how much the agents will deviate from this reference policy. And if you don't have anything to encode, then you can simply just put a uniform policy here just for the regularity. So the representative agent can then easily find an optimal policy for this single agent optimization problem. And this optimal policy pi star will then be applied by all other agents. And then this will induce a new mean field because now we have changed the behavior of this of the whole population. And this new mean field will give us a new MDP with an induced reward. And we have basically closed the loop. So you start with a mean field, you get a optimal policy under that mean field. And then from that optimal policy, you induce a new mean field. And then now you have to re-optimize again. So the objective here is to find a consistent pair of policy and mean field such that the policy is optimal under the mean field and the mean field is also induced by this optimal policy. So with the entropy regularization, we were able to prove that with a properly selected beta, the above iteration basically find the optimal policy, induce the mean field, get a new reward, and then optimize again. This iteration is indeed a contraction, and then it will converge to a unique consistent pair. And we can show that this will produce a Nash equilibrium for the infinite population. So the policy we have found here select an action based on the current state of the agent. And it also implicitly depends on the mean field, since we already know the mean field, how the mean field will behave if all other agents apply the same policy as we are doing. So when the system is actually deployed to the field, an agent only needs the observation on its own state to select an action because it's an implicit dependence on the mean field. Now we have solved the policy for the infinite population system, and we want, but our ultimate goal is this n agent system, right? Because in reality, there is no system that has infinite number of agents. So we will let all n agent in the finite population to deploy the policy that we have just found. So the next question we obviously will have is that what kind of performance guarantee do we have for the n agents applying the policy we found for the infinite population? So this leads to the main theorem of this work. So this theorem basically states that if agent I deviates from the optimal policy pi star that we found for the infinite population system, then while all other agents, all n minus 1 agents are still applying the policy we just found, then agent I can gain at most a small amount of performance. And then that small amount of performance decreases with an order of square root of n. In other words, the performance gain diminishes as n approaches infinity. So essentially, what we have found here is an ipsilon Nash policy for this n agent system. So we finally apply this framework to a dynamic resource allocation problem over a graph. So we have a population of robots deployed to a graph, and then they can traverse along the edges and move around the nodes. They will receive a terminal reward at the terminal time step if they are at node 3, and an agent will receive a 1 unit of reward if it is at node 4. So aside from these rewards, the agent also get penalized for high population density at each node. So with this penalty, the agents should not all concentrate on node 3 for the high reward. They need to decide how they are going to split among the 2 nodes. Again, just want to emphasize that in this formulation, all agents are selfish, and this is not a team game, and each agent is just maximizing its own cumulative reward. So if we do not perform the entropy regularization that we have discussed before, the robots cannot reach a consensus on how to split among node 3 and node 4. So from one iteration, the agents will all concentrate on node 3 for the high reward, and then they all get penalized for this high population density. And then at the next iteration, they all switch to node 4, and then they all get penalized, and then they go back to node 3 because node 3 from the last iteration's experience has a lower population density. So they will just oscillate between the 2 nodes, and then the algorithm will fail to converge. So in our formulation, we can give the agents a reference policy. And then in this case, we give the agents a reference policy to distribute evenly over node 3 and node 4. And obviously, the algorithm converges. So the following 2 figures basically present the population behavior over time. So this axis is time, and then this is the state. And then the z-axis is basically the population distribution over these states. So we tested with 2 inverse temperatures, or betas. So when beta is large, or in this case, beta equals to 3, we're giving less regularization, and the agents show a preference toward node 3 here over node 4. They concentrate on node 3 till a point when any additional population on node 3 will incur a population density penalty that diminishes the reward advantage that they have over node 4. On the other hand, if we give a small beta, this is basically more regularization, then agents respect more the reference policy than the reward, and then they would just distribute evenly over the 2 nodes, which is essentially the reference policy. So essentially, we can shape the population behavior by playing the reference policy and the inverse temperature beta. So different from directly forcing the agent to follow a reference policy, which we can always do, this approach, or this mean field approach, still gives the agent some autonomy to decide its behavior based on the rewards. And we can change the level of this autonomy through beta. So the very last figure here shows a log-log plot of the performance gain versus the number of agents. So indeed, the performance gain obtained by the agents by unilaterally deviating from the policy that we found diminishes with a rate bounded by 1 over square root of n. At the horizontal axis, we have the number of agents, and then the vertical axis, we have the performance gain by unilaterally deviating. And this reference line has a slope of minus 0.5, which is basically the line for the order of 1 over square root of n. So this basically verifies our claim for the epsilon Nash. Finally, I just want to give a quick recap of this mean field approach. So we first approximate the n-agent system with an infinite population system. We then find the Nash policy in the infinite population through this representative agent. We then let the n-agent in the finite population deploy this Nash policy, and then we show that in this case, the policy is still an epsilon Nash policy. So that basically concludes part 1. Now we can go to part 2, addressing the large state space issue. So we will introduce a hierarchical decomposition approach to decompose a game with large state space into a bunch of much smaller games. So in this case, we will focus on the 2-agent zero-sum game, which is a special case of the n-agent game. And we define it through the following tuples. So we have 2 individual state space, 2 action space, and a transition function, a reward function, a single reward function, and a discount factor. So the reward function is the same for both of the agent in this case, but instead of having both of them maximize the reward, we will have agent 1 maximize and agent 2 minimize. So to solve this Nash equilibrium for such game, we have a very classic iterative or Nash solver, or essentially a value iteration algorithm, or also known as the shape-leaf method. The following is essentially the update rule for this algorithm. The key step here is the value update of the Q value update. So it's essentially just solving a matrix game here. And then this max-min game can be easily solved or casted as a linear program. And we can easily solve this kind of a matrix game. So this is not a real problem for us because we have all these efficient algorithms such as simplex method and the interior point method that can really solve the game. However, the issue really comes from the fact that this max-min optimization needs to be performed at each state, at each iteration. So for example, and then this becomes a trouble or a challenge when we have a large state space. So for example, the pursuit-evasion game that we will talk a little bit later has almost 1 million joint states for this game. And then as a consequence, then every value iteration, we need to solve almost 1 million linear programs. So it's really burdensome for the algorithm if we directly apply this value iteration algorithm. So in this part, we will just try to answer this question. Is there any way that we can reduce the number of this kind of max-min optimization that we need to perform at each value iteration? So our answer to that is through a hierarchical decomposition. So I want to quickly motivate this decomposition scheme. So we will focus on the pursuit-evasion game here to give a better understanding, even though the approach proposed here is more general than this. So in this pursuit-evasion game, the pursuer, or this red dot here, is trying to capture the evader, the green dot here, by being in the vicinity or try to get the evader into its capture radius. And then the evader tries to avoid that kind of capture. So the question I want to ask is that if you are the pursuer, how would you make decisions in such a large state space? So some further questions: Do you always need the same fineness resolution all the time? And the next question is that is it really necessary to update your decision at every time step? For me, suppose the evader is far away from me, which is the case presented here. Which room the evader is in may already contain enough information for me to make a decent decision. All I need to consider is which neighboring room I should visit at the next time step in order to close up the distance given the current situation. However, when the evader and I are in the same room, then maybe I should really restrict my attention to this single room here and consider the exact position of my opponent, basically the evader, so that I can do the fine maneuver, try to capture the evader. With this intuition, we are essentially creating a hierarchical framework in which we make decisions with two different resolutions of the state space. So based on this intuition, we temporarily break down the game into two phases. So in phase one, the game is played at a room level. So in this case, we have 9 rooms, and then the phase one aggregated game will also have like 9 positions for each of the agent. And then the agents are going to select options to navigate to a nearby room instead of to navigate to the nearby position. We will talk more about the options framework later, which is a generalized action for the superstates. Essentially, we're treating the room as the aggregated states or the superstates of the agent, and then pursuer tries to be in the same room as the evader, and then the evader tries to stay away from the pursuer in this phase one game. Once the two agents are in the same room, then we enter this phase two, a local pursuit-evasion game. The agents will directly select their primitive actions, up, down, left, and right. And then the local game is just a standard game, but restricted within a single room. So if the evaders escape the room, then we will transition back to this phase one game. So you can see that we have two resolutions here. So in the local games, where the agents are observing the exact position, and then in the aggregated game or in the phase one game, they only observe which room they are located in. So we can also see that the local games and this room level game have much smaller state space than the original game. So the original game had 56,000 states, and the phase one game has 81 states. And then for the local games, we have different rooms, but roughly speaking, they all have around like 600 states. So it's a much smaller game. And also, just one more note, we can formalize this definition of rooms through superstates. And this approach can be easily extended to more general games, but we will just keep using the rooms and just focus on the pursuit-evasion games for convenience. Now we can really talk about the option framework. So in the original game, agents will select a primitive action, basically up, down, left, and right, to transition to a new state or a new position. In other words, the primitive action serves the role of taking agents from one state to another state. Now we want to play an aggregated pursuit-evasion game at the room level. Naturally, we will want to extend this notion of action so that by selecting this generalized action, the agent can transition to a nearby room. So this idea of generalized action can be formalized through this option framework, and an option is essentially just a tuple that contains the domain of the option, which tells the agent when or at which state this option is available, and then a set of states or a set of terminal states that is telling the agent, if you reach one of these states, then this option is terminated, and then you need to select a new option. And then finally, a local policy that is telling the agent what action should I pick if under this option, given that I'm currently within the domain of this option. So for the pursuit-evasion game, we want to generate the options that would navigate agent from one room to a neighboring room. So in a more general stochastic game, we generate options that help agent to transition from one superstate to another superstate. So the two figures here presents the policy for the option room 7 to room 4 and room 7 to room 8. So these little arrows basically represent the local policy, and then they show which direction the agent should go at each location under these options. And also these red cells are the target state in target neighboring room. So in this case, these target state are in room 4 for this option. So these options are generated in agent's individual state space, and they can easily solve from a single agent MDP or a single agent Markov decision process. So it's a single agent problem. So we can set the state within the room as the domain of the option, and then all the state outside this room as the terminal set. And we can also assign a positive reward for the target state within the target room. And then we basically just form a local Markov decision process, and then we can just solve this MDP, and then we can find a policy for this option. So once the agent select an option, the option will execute this local policy till reaching the terminal state, in this case, leaving the room. So essentially, another way to look at the option framework is that the option is some kind of pre-computed behavior or low-level control laws. And then by using this option, the agent is essentially reducing the frequency of its decision making. So more specifically, if I select which room I'm going to visit next, or essentially if I select one of these options, then how the primitive actions are selected is really up to the option policy, not really up to me. So it's more like an intuition thing. And I will only update my option selection once I reach the room or once I leave the room. The following two animations here shows the options in work for these two options. For the pursuit-evasion game, we're just going to generate options for agents to navigate from all rooms to their nearby rooms. And then these options that we solve will be the action for the aggregated pursuit-evasion game that is played at the room level. Now we can discuss the overall hierarchical approach. So we have started with the original game, which has each cell or each position as the state for the individual agent. Through the abstraction and the option framework, we will generate the aggregated game, which is played at the room level. The agents observe the current state, and the agents in this room will observe its current room and also its opponent room, and then select options to navigate to a nearby room. So for the 3x3 example, we have a total of 9 rooms, and the state space of this aggregated game has 81 states, or basically 9 squared states. So the goal of the pursuer here is to be in the same room as the evader. And then when the two agents are in the same room, we transition to a local game that is restricted within a single room. So the local pursuit-evasion game has a restricted state space within a single room, and the local game ends with a capture if the two agents are within the capture radius, and the evader evades if it successfully escaped the room without being captured. And then in this game, the agents directly select their primitive actions up, down, left, and right, and stay. And then if we actually have an escape from the evader, then the game transitions back to phase 1. So the aggregated pursuit-evasion game basically corresponds to the decision-making process at a coarse resolution of the state space, and this decision is updated less frequently. And the local game corresponds to the decision-making at the fine resolution, and at every time step, the agent actively selects their primitive actions based on the exact position of the two agents. So to connect these two processes at different resolution, we conduct a value propagation. So we will first solve the Nash values for each of the local games, 9 local games in this case. Then we will use these Nash values as the terminal reward for the aggregated game. So through this approach, we have significantly reduced the cardinality of the state space. So the original game has 56,000 states, and then by this decomposition, we get one aggregated game played at the room level with 81 states, and then 9 local games, each within a room, and then each with roughly 600 states. So the end product here are the aggregated Nash policy, which that is operating at the room level. In other words, this aggregated Nash tells the agent which option to select given the current room and its opponent's room. The local game, from this local game, we will get a local Nash equilibrium within each room. This Nash policy tells the agent which primitive action to select given the exact position of the two agents within the room. So when we execute the hierarchical policy, we will start with the aggregated game, and then an agent will first select an option to execute. And then the option select the primitive actions given the exact location within the room, and then this option selected will be active until the agent leaves the room, and then at a new room the agents will update its option selection. So we will transition to a local game if the two agents are in the same room. And then when in the same room, all agents deploy the local Nash policy, which is computed within that room. And then this Nash policy directly selects the primitive action. And then the game ends if the evader is captured. And then we transition back to the aggregated game if the evader escaped the room. Now, finally, we can present a trajectory or an animation of the execution of the hierarchical policy. So in this pursuit-evasion game, we give the pursuer a slightly faster speed and the evader a slower speed. How they can move is basically depicted in this reachability set here. So in this animation, we will also have these cells that are masked with the agent's color. Those are the target states for the agent's option. So right now they're in the aggregated game. They're just selecting the options, and then now they are in the local games, and then the game ends with a successful capture. So we now present a comparison between hierarchical approach and the flat Nash approach, or the Shapley's method, which directly solves the Nash equilibrium with the original large state space. So the first comparison is on the computation side. This is the computation time comparison with the horizontal axis as the cardinality of the state space, and then the vertical axis is the computation time in second. So we can see that the computation time of the hierarchical approach increases much slower than the flat Nash approach as the game gets larger. The other matrix we use here is the number of matrix games solved, solver called, and then this is also increasing much slower than this. So another observation is that if we look at the log-log plot, we can see that at the very beginning, when the game is small, the hierarchical approach actually spends slightly more time than the standard approach because all these decomposition doesn't come free. We need to perform an auxiliary task in order to construct these local games and aggregated game. So that really reflected here. And then on the performance side, we use the average number of steps till capture as the performance metric. We can see that when we use hierarchical pursuer playing against the Nash evader, there is a performance drop comparing with a Nash pursuer versus a Nash evader. So essentially, it takes longer for a hierarchical pursuer to capture a Nash evader than a Nash pursuer to capture a Nash evader. So this is as expected because we're saving a lot of computation time and performing the abstraction. And at the same time, this approach is really addressing the large state space. So one may not even be able to solve a Nash equilibrium for a large game when the game gets really large. So we stop this comparison at 6x6 game, essentially just because we cannot solve the Nash equilibrium for an even larger game. But the hierarchical approach can easily extend to much larger game up to like 15x15. So now I just want to quickly talk about the cause of suboptimality here. So this is not a random string. So this is the famous principle. There is no such thing as a free lunch here. We will first present two animations, or on the left is a hierarchical pursuer against a Nash evader, and then on the right is a Nash pursuer against a Nash evader. So let's just take a look at the trajectory. So the blue dot is the evader. And then this is the suboptimality just appear. We will see next. So this is a Nash against Nash. So this is a really boring trajectory. To me, it's just the pursuer is utilizing its higher speed to capture the evader. So the interesting here is actually at this moment. So the pursuer is at this location, And it could have just directly chased down the pursuer down here, but instead of doing that, it decided to come down and then go along this trajectory here. So what happened here is that the pursuer, the hierarchical pursuer, is still playing the aggregated game. And then in that case, it's only observing the room, which room the evader is in, and then whether the evader is actually here or somewhere else is really unknown to the evader, or it's irrelevant for the decision-making process in our framework. So instead of directly tracing it down, the pursuer considered the possibility that the evader could be somewhere down here, and then it really gives the, if that's actually the case, then directly tracing down from this corridor here may not be a smart idea. So that's why the evader, the pursuer decided to go down and then defend this room, and then by basically blocking the evader. So in summary, we want to just argue that there are at least two causes for the suboptimality. So one comes from the information loss in the abstraction. So more specifically, when agents make decisions based on the room information in the aggregated game, instead of considering the exact location, there is information loss, and then there's no way we can recover that. The other one is a less frequent decision update. So the hierarchical pursuer only updates its option selection when it reaches a new room, while the Nash pursuer updates which position or which action it's going to select every time step. So the Nash pursuer can respond faster to the evader's position or location change than the hierarchical pursuer. With this, I have basically concluded part 2, and then I just want to give a couple thoughts on the future directions. So for the mean field games, we're considering a mean field team game formulation where we have two teams competing in a zero-sum manner, while within the team, the interaction is modeled as a mean field game. And then another extension we're looking at is an online learning version of the mean field game, such as a multi-arm bandit problem where the rewards of agent receive by pulling an arm depends on how many other agents have pulled the same arm. So this has some kind of cool application in the stock market, and I'm really interested in earning money on that. So for the hierarchical decomposition, we're extremely interested in this automatic superstate or room generation. In our formulation, the rooms are basically given to the algorithm, or we as the human use our domain knowledge and our intelligence to give the algorithm the partition of the state space. So one method we're looking at right now is the proto-value function, which relies on the graph Laplacian operator. So this figure here shows a proto-value function for this 2x2 room environment. And then one can see that the geometric relationship between the states is somehow already reflected in this proto-value function. So another direction is to extend this framework to a multi-agent scenario with more than 2 agents. This will be challenging as how to construct the local games and deciding which of the agents should be considered as the active agents within the local game. These are still unknown to us, or it's relatively unclear. Yeah, finally, just a recap what we have covered. So we use the entropy-regularized mean field to address the number of agents issue, and we use this hierarchical decomposition approach to address the large state space. So again, it was quite hard a decision for me to make whether I should just dive deep into one of these single topic or cover both of them. But I decided to go with breadth first presentation, and I hope at least I have convinced you that the scalability in the multi-agent decision-making problems is indeed an interesting topic. So with that, I have finished my talk, and I would like to thank you for your time, and I'm ready for questions.
Great, thank you, Scott. Very interesting talk. I'm excited. Like, I'd like to see the mean field combined with the hierarchical structure. That seems cool. I have a question. So, like in the mean field formulation, you represent the total population as a single like mean point. How do you like see the splitting action of like some of the population knows to move to 3, and then some of the population knows to move to 4, for example?
Yeah, so that's a great question. So what happened here is that the end result here will be a stochastic policy. So basically,
okay,
all the
yeah.
agents are going to apply the same policy, and then they're going to say, if I'm at state 2, for example, then 50% of the time I'm going to know 3, 50% of the time I'm going to know 4. And then when you have a large number of agents, it's automatically split the agent into 2 groups.
No, interesting. Yeah, because I do like the idea of stochasticity, because stochasticity kind of helps this type of cooperation between teams and all. Because if everyone's deterministic, then yeah, exactly. Like everyone would probably end up at node 4, but stochasticity allows that diversity of the policy. Very cool.
Yeah, I totally agree. And also stochasticity, or like these kind of mixed strategy, give a better mathematical characteristics. For example, it's more like a convex hull of a bunch of extreme policies instead of like the deterministic policy or just like single points in the policy space. Yeah,
definitely. Cool. Anyone else have any question? Oh, Victoria, go ahead.
Yeah, hi. Thank you so much for the talk. It was super interesting. I'm curious if you've considered the influence of delay. A lot of classical mean field modeling outside of like this mean field game structure has shown that you can model the team or like the particles as like the center of mass, but that when you actually start thinking about how long it takes for information to propagate through the team, that information inherently has delay and can cause different points of instability. And so I was curious if you had seen some of those different dynamics, behaviors that arise here in this mean field game in the same way because of potentially noise that is introduced through delay, or maybe even more so just more generally, what happens if you have noise in the positions of your particles in this mean field estimate? Is it easily perturbed or is it relatively robust to that?
Yeah, I see. That is a really good point. So right now in this formulation, the mean field is essentially deterministic, or when the number of agents gets large, the mean field, we don't really need to observe the mean field because we know if all agents apply this same policy, we somehow already have an estimate of how this mean field or how this population will behave. So that's where this implicit dependency comes into play. But what you are saying is a very interesting research direction, I think, because in reality, if we really want to train the system instead of directly solving it, either the dynamics is unknown or when the state space is too large, reinforcement learning algorithm really can help with this situation. Then, just like what you said, there is a delay in this mean field propagation. Or the mean field information propagation, because all agents can only make their local observation, and then when they really sense the difference in this population behavior, it may already be a delayed thing. Yeah, I totally agree with you. Right now, I don't have a good answer whether it is that easy to introduce it into the classic mean field game formulation. I do believe we can introduce it, but how much instability it will introduce to the system, I don't have a good answer right now, but that's definitely something interesting to think about. Thank you.
Cool.
Yeah, thanks.
Yeah, thank you for your answer. If no one else has a question, I have another one. If you have time to answer another one.
Yeah, I have time. Yes, thank you.
I am curious if some of your assumptions about the agents all being homogeneous so that they have these identical state action spaces. We've seen some research out of biology, so thinking like Naomi Leonard and other people who have studied some of these natural systems, that in fact there are potentially situations where natural leaders emerge. And so that there might be, and this is definitely true in the migration case. In the starling case, you actually end up seeing the birds are reflective of the chorus line because they're only actually able to respond to starlings, I think it's 8 of their neighbors. And so the chorus line is this hypothesis that you can anticipate what your neighbor is going to do and react accordingly. And that's what allows some of these really fast fluctuations. Knowing this from the biological standpoint, do you have concerns about these homogeneity constraint or assumptions that you're making? And are you thinking about what weakening these assumptions might look like in terms of your mean field game?
Yeah, that's a great point. So literature already exists on these kind of so first of all, the answer is two parts. So directly on the homogeneity part, we can actually easily extend this mean field game to a heterogeneous group by introducing different types of agent. And then, for example, if we have k types of agents, then we will have k representative agent, one for each of these types. But the key idea here is that among these k types, all agents need to be homogeneous, and then we need to assume that these k types of agents are also of large population. So that can be easily addressed. For the next point regarding the leader, in this kind of animal behavior or a large animal population, there are also like work on something called a major minor mean field games. Where basically emerged from the background of finance, where you have a bunch of individual investors, but you have like a huge financial institution, and then this huge financial institution's decision has a huge impact on the rest of the individual investors, and then but the individual investors are just like a large population, and then each of them has a ignorable effect on the mean behavior. And then in that case, you can also formulate the mean field in that extent. But when you have a mediocre large number of these kind of leaders in the system, then it becomes really tricky for the mean field to handle. So the mean field can really handle like a single or like 2 or 3 large leader or like significant leader agents, plus a bunch of insignificant mean field population, but it cannot really handle like if you have say 20 leaders in this game, but like 1,000 little agents down there, then it becomes an issue. But if you are just interested in like couple leaders, then I think it's totally fine. I wouldn't be concerned.
Cool. Thank you very much.
Does that answer your question?
Yeah, no, it does. Thank you very much.
Any last questions? I think we're out of times, but I want to say thank you, Scott, for your presentation, and definitely very interesting.